Non-Commutativity of function composition. Welcome to this lesson on the non-commutativity of function composition. Let's start by establishing some foundational terminology. In mathematics, we describe a binary operation as being commutative if changing the order of the operands does not change the final result. To put this simply, think about basic addition. Addition is commutative because a plus b equals b plus a. The order of the numbers doesn't change the sum. The same logic applies to multiplication. Multiplication is also commutative because a times b equals b times a. However, it is very important to note that when we deal with the composition of functions, this property generally does not hold. In other words, you cannot simply swap the order of the functions and expect the same answer. In this subsection, we will explore exactly why the order in which we apply these functions matters. We will demonstrate that, in most cases, the composition of functions is non-commutative. Over the next few slides, we will use a real-world analogy and a mathematical example to show you exactly how this works in practice. Understanding the concept. Now that we have established what commutativity means and why function composition generally lacks this property, let us dive deeper into how these compositions actually work. First, let's look at the notation. When we write g circle f of x, it is read exactly as g circle f of x. Mathematically, this is equivalent to writing g of f of x in this process. It is crucial to remember that the function f is applied to the input first, and then the function g is applied to the resulting value of f. Conversely, if we reverse the order and write f circle g of x, it means f of g of x in this scenario. The sequence is flipped. The function g is applied first, and then the function f is applied to the result of g. The reason this is so important is that the inner function changes the input before the outer function can act upon it. Because the second function is processing a different value than the first one did, the final output is usually different. To help you visualize this concept without the math, we will move on to a real-world analogy involving socks and shoes in the next slide. Real-world analogy, the socks and shoes example. Now that we have established the mathematical definition of function composition, let us use a real-world analogy to make the concept of non-commutativity more intuitive before we dive into the formal proofs. To understand this without complex math, consider two daily actions as functions. Let us define function f as the action of putting on socks and function g as the action of putting on shoes. Let us first examine scenario A, which is the composition of g circle f as we discussed in the previous slide. The function on the right is applied first. Therefore, we first apply function f, which is putting on our socks, and then we apply function g, which is putting on our shoes. The result is the correct and intended outcome. Your socks are inside your shoes. Conversely, let us look at scenario B, the composition of f circle g in this instance. The order is reversed. We first apply function g, meaning we put on our shoes, and then we apply function f, which means putting on our socks. The result here is very different and logically incorrect, as your socks would end up on the outside of your shoes. Since the final result depends entirely on the order in which these actions are performed, we can say that this composition of dressing is non-commutative. This illustrates that changing the sequence of operations leads to a different output. Now that we have a conceptual grasp of this, let us proceed to the next slide to demonstrate this principle using real-valued mathematical functions. Mathematical demonstration. Now that we have explored the concept through a real-world analogy with socks and shoes, let us move on to a formal mathematical demonstration to prove that function composition is non-commutative. To do this, let us consider two real-valued functions. We are given f of x equals x plus 5 and g of x equals 2x. We will begin with step 1, where we evaluate g circle f of x first. We start with the definition, which tells us that g circle f of x is equal to g of f of x. Next, we substitute the expression for f of x into the equation, which gives us g of x plus 5. Now, we apply the rule for function g, since the rule for g is to multiply the input by 2. We write this as 2 times the quantity x plus 5. Finally, by distributing the 2, we simplify the expression to 2x plus 10. Now, let us move to step 2 and evaluate the composition in the reverse order. F circle g of x, starting again with the definition, f circle g of x is equal to f of g of x. We then substitute the expression for g of x, which gives us f of 2x. Now we apply the rule for function f, which is to add 5 to the input. This results in 2x plus 5. Finally, in step 3, we compare our two results. The result of g circle f of x is 2x plus 10, while the result of f circle g of x is 2x plus 5. Since 2x plus 10 is not equal to 2x plus 5, we have successfully demonstrated that g circle f of x is not equal to f circle g of x. This mathematical proof confirms that changing the order of the functions changes the final output. Keep this in mind as we move to the next slide, where we will discuss some common mistakes to avoid when performing these substitutions. Common mistakes to avoid. Now that we have mathematically demonstrated how the order of operations changes the result, it is crucial to address some common pitfalls students often encounter when solving these problems. First, be very careful not to confuse function composition with function multiplication. A common error is treating g circle f of x as if it were g dot f of x. It is important to remember that multiplication, which is g of x multiplied by f of x, is commutative, meaning the order does not change the result. However, composition, which is g of f of x, is not commutative. Secondly, avoid the assumption that the order of composition does not matter. Some students assume that if they have already found the result for g of f of x, then f of g of x must be the same. As we saw in our socks and shoes analogy and our previous mathematical example, this is rarely the case. Therefore, you must always calculate both compositions separately to verify the results. Finally, let's discuss the process of substitution. When you are calculating f of g of x, a frequent mistake is incorrect substitution. To avoid this, ensure that the entire expression of g of x is substituted into every single instance of x within the function f. Keeping these common errors in mind will help you maintain accuracy in your calculations. Now, let us move to the final slide to summarize the key takeaways of this lesson. Key takeaways. To wrap up our lesson, let's go over the key takeaways to ensure you have a solid grasp of this concept. First, let's revisit the core definition. We have established that function composition is non-commutative. In plain terms, this means that, in general, g circle f is not equal to f circle g. As we discussed when breaking down the process, the order of application is critical. In the expression g circle f of x, the function f, which is the rightmost function, is always the one applied first, before the result is passed into function g. This brings us to the idea of dependency. As we saw in both our socks and shoes analogy and our mathematical demonstration, the final output of a composite function depends entirely on the specific sequence of operations. Changing the order changes the result. Finally, it is important to note that while composition is generally non-commutative, there are a few special exceptions where g circle f does equal f circle g. This occurs in specific cases, such as when one function is the inverse of the other, or when one of the functions is the identity function, denoted as I of x equals x.